So molecular ionic and net ionic equation. So this is for reactions between ions. So let's say I add like a NaCl and silver nitrate. So the molecular equation would be treating ionic compounds as molecules. So I recognize that these two compounds are ionic because I have a metal and a nonmetal, right? I have Na, metal, Cl, nonmetal. I have Ag, metal, NO3, group of nonmetals. So when I have a metal and a nonmetal, I know it's ionic. I know it's held by an ionic bond. It's not really a molecule, right? Because in a molecule, all the atoms have to be sharing electrons. Ionic bonds involve charge attractions, not shared electrons. So it's not really a molecule, but the molecular equation is showing the ions as if they're stuck together. So the molecular equation is not reality. And I don't really like it because it's not reality. If I show NaCl aqueous, aqueous means it's in water. If it's in water, the ions are not together. When I dissolve an ionic substance in water, the ions don't stick together. If it's dissolving, if I put the ionic substance in water and it's not dissolving, that just means I have a chunk of solid that sank to the bottom. It's solid because the ions are still stuck together by their ionic bonds. If it dissolves and I don't see the solid anymore, it's because the individual ions separated from one another and are able to move around in solution. So really, the ionic equation is a better way to represent that because it shows the ions separated it allows me to see that if all those ions separate because everything dissolves, now I have the opportunity for particles that weren't initially together, if they are oppositely charged, to come together and attract. So there are a bunch of rules to predict whether things will stay dissolved or whether they will form solids if the ions come together and attract. I don't expect you to memorize those. I'm not going to ask you questions about them. In this particular example, however, the silver and the chloride attract effectively, so they would come back together and form a solid. The attraction between silver and chloride is pretty strong attraction compared to the NaCl or the AgNO3. I wouldn't expect you to predict that, but if I gave you the full reaction, just showing what the reaction would look like as an ionic reaction versus molecular. And then the other two ions left that don't come together are the Na and the NO3. So the top equation is a molecular equation because this shows everything together as compounds. Unfortunately, it's not really accurate because I know if something is aqueous that the ions are not together. They're separated and surrounded by the solvent. So the ionic equation does a better job of showing that because it shows all the ions separated. So this is real life. That's what's really happening. However, the molecular equation is nice. It does have one advantage, and that is that if I wanted to do this reaction and make silver chloride, I wouldn't go to the chemical catalog and order Na+, because that doesn't exist by itself. I would go to the chemical catalog and order NaCl and add that to water, and then I would order AgNO3 and add that to water. Then the Ag and the Cl would be able to come together and form a salt. So the molecular equation does show what the compounds would be if they weren't dissolved in water. The ionic equation recognizes that when I dissolve something that's water soluble and it's ionic, the ions separate, and so I show them separate from one another. Then the net ionic equation is like the ionic equation, except it's focusing just on what are the particles that are actually undergoing a change. So once I have the ionic equation, I can see that anything that appears on both sides in the exact same form is not really doing anything here. If I start with Na plus in solution, surrounded by water, and I still have the Na plus just surrounded by water, it's not really undergoing a change, so it's not really important to what the actual change is that's occurring in this reaction. So I can cancel it out. And when I write the net ionic equation, I take the ionic equation and cancel out anything that appears on both sides in the exact same form. And so I can also cancel out, oh, I made a mistake, sorry. This should have been NO3 minus. Because the Cl and the Ag came together, what's left is the Na and the NO3. So I also then see that the NO3 is in the same form on both sides, so that cancels out. So the net ionic equation would just be the ions that are actually undergoing the change, and it would show exactly how they're changing. So they're going from being in solution to sticking together, forming their ionic bonds in the form of a solid. All three of these show the same thing happening. Just three different ways of showing that. Other question?
How would we be able to recognize a precipitate?
I don't expect you to predict when a precipitate is going to occur. I expect you to be able to, if I give you a reaction, recognize it as a precipitation reaction. That's pretty straightforward. If you have everything dissolved, or all the ions separated, and then you see a solid forming as a result of the reaction, that's a precipitation reaction. So if I give you that full reaction, you could label it as a precipitation reaction. You could say, this is telling me that the silver and the chloride form a much stronger ionic bond than any of the other ions present there. That's why they are able to find each other, and when they come next to one another, they stick together, and that's why I form a solid chunk of that where the ions are organized plus minus in making their attraction.